what's the equivalent capacitance?
Do you add the ones in parallel first? And then see?
Yeah, that's.
That would be 2.4 farads.
You got 2.4? Anyone else get a different number?
I want the same.
Okay. Anyone else get a different number? See the answers I can come up with. Do I get 1.9? Anybody get 4.5?
Let's see, that one, all right, so we
Anybody get 4.75? I haven't done yet. .63. All right, so what other answers can I get? Let's see, so. I assume this is, I got 2.38, was that what, the 2.4 that you got? I had 2.38. I think I've got one more answer I can pull out of this. And then let's talk about why all of these, assuming I didn't make a careless error, why all of these could be correct answers, given the problem I gave you. And then 2. Now, I would not be shocked, would be shocked if I did not make a careless error. However, how could I get multiple answers on this problem? I've asked some test problems, I've given something like this and said, what's the maximum capacitance? What's the minimum capacitance? So how'd you get 2.4? Assuming you did it the same way.
I wasn't exactly sure how to do it, but I did the 1 plus 3, then 2 plus 4, 1/4 plus 1/6 is 10 over 24, so 24 over 10 equals 2.4.
Oh, okay. You did similar? All right, that actually is not legitimate, what you did. I appreciate your being brave enough to talk about it. Why is that? Because the first thing you did was you added the 1 and the 3 in parallel. Why is that not parallel? What's required for parallel?
Junction.
Yep. And?
The battery?
Pardon?
The battery?
Oh, no, you don't need
Okay.
necessarily need the battery to get equivalent capacitance. All right, so if I have 1 farad and 3 farads, they are clearly in parallel there. I hope that's clear that they're in parallel. There is indeed a junction at each end, and there's nothing in between the junctions except for the 1 and the other path, the 3. But if you're putting 1 and 3 in parallel here, well, how are you handling these? What you did was one, 3, 2, and 4. You did those in parallel, you did those in parallel, but these can't be in parallel because if you're considering those junctions right there, I do have something in between. But what I just did does give a hint to why I have multiple solutions.
The second way I did it, I got the 1.9.
Got the 1.9? And I forgot how I did that one. What did you do for that?
For that one, I treated the 1 farad and the 4 farad as in series, and the 2 and 3 as in series.
All right. If instead of doing that, you treat the 1 and 2 as series and the 3 and 4 in series, you have 1 plus 1/2, which is 1, just 3/2. So that would be 2/3. And then 1/4 plus 1/3 is 7/12. So this would be 12/7. And so that's 36 and 14. So that's 50/21.
That one.
That's a
2.38.
That's a 2.38? Okay. Given the problem is Austin's 1.9 farads more or less or the same or equally legitimate to this 2.38 or 2.38. Which one of us is right? Austin, were you right what you did?
I think so.
Good. But not confident?
Still don't exactly know how it works, so.
All right, spoiler alert. We're equally right.
Is it
I did not give enough
variable?
information. Pardon?
Is it variable and something like that?
What if I set up this situation in the lab here and we were throw a micro in front of it to make it safe, and I wanted to find equivalent capacitance, where I put the leads matters. If I put the leads here and here, these are in series, those are in series, this set is parallel with this set. So you do series first and then add them in parallel. If you put the leads here and here, Now these are in series, and then this structure is in parallel with that structure.
So just because you have the same values, if you change where you're measuring from, it'll get different values.
Which is why on the lab, when I gave you the capacitors and asked you to come up with something within a target, you need to tell me where the leads are. Because if you give me a structure like this without knowing where the leads are, there are 6 different answers here that are all legitimate. And the other ones I got by putting here, and then here, and then here, and then here. So that was the point I wanted to make, is that when you're drawing circuits or designing a circuit, it does matter where the leads are.
Sorry, where did you put the leads for the other ones?
So putting them here gets you the 2.38. Putting them here gets you 1.9. Getting them here gets you, I forget which one that is. Then putting the leads here, putting the leads here, putting the leads here, gets you the other 4 answers. Barring Carol's errors. Because if I put the leads here, that 1, 2, and 3 are in series now. And that 1, 2, 3 series is in parallel with the 4. So it add the series up first, and then add the parallel for the 4. Questions? All right, now it's time. Spherical and cylindrical conductors, or capacitors. Let's start with cylindrical. So from an end view, it looks like that. I've got, instead of the parallel plates, I have a charge. And just for the sake of keeping even with my notes here, I think a positive charge I have in the middle traditionally. Yeah. So this is positively charged here, and this is negatively charged there. There's empty space in between this, so this is empty.
Is that like a top view?
Pardon?
Top view.
In view. You've cut it, now you're looking at it. Cylinder, it's a cylinder. So from a side view, so this is side, this is view, and in view.
Where are those positive and negative points? Is it on
So this inner conductor is positively charged, and the outer conductor, outer sleeve, you might want to call it, is negatively charged. I am assuming it's empty space in between. In reality, if I were designing this, I would need some material in order to keep this from touching the side. Otherwise, it would just immediately discharge. So you'd have some dielectric in there, but I'm going to ignore that. We could magically, because this is a board problem, we could magically just have it suspended there in the middle. Or maybe they're driven in the ground. These things are just it's a rod and a stiff annular cylinder. We will assume that the inside has a linear charge density of sigma, and the outer one has a linear charge density of negative sigma. Again, it's a capacitor. We do want the similar charge on both, just one's negative, one's positive. I know that capacitance, I can't use the kappa epsilon naught A over D because that's specific for parallel plates, but I can use Q over delta V for finding the capacitance of this. So usually on problems like this, Q is not the hard part, delta V is. So we need to figure out what is the potential difference between these two cylinders. between the inner cylinder and this annular cylinder on the outside. Well, let's figure out the electric field. And once again, for contrast, I grabbed blue. All right, so what is the electric field in between the two? I know it's going to go from positive to negative. What is the electric field? Chapter 24. Any of you familiar with the Saxon series of math books? Saxon was I don't know what his first name was, but or he is. He was a math teacher, and he got tired of asking questions of students where, they'd been tested on it, but once they were tested on it, they just forgot. And so he developed a math curriculum where there's constant reinforcement. The problem that you do with the first chapter, you'll still be seeing those problems throughout the entire course. So what I was thinking of, the memorization quizzes, this part of me thinks, let's just throw in some of the stuff from the previous chapters just to see what happens. I know what would happen for me as a student. I would forget them as soon as I'd taken the quiz, but there's still part of me. I'm not going to subject you to it. That'll be the next class. Don't worry. But I'll make sure they know where each of you live. All right, electric field. Think of it this way, infinitely long wire. This thing is a really long cable. The electric field coming from an infinitely long wire.
Is it the one that we derived?
Yes, we did.
1/4 pi epsilon naught lambda L over R.
Close. All right, that's the one. 2 pi.
It's 2 pi, okay.
So not pi. We did it the long way with force. What is the force on a charge? The distance, infinite distance away, and then we use Gauss's law to derive it for electric field. All right, so that's my electric field. So how do I find the voltage?
Is this cylinder infinitely long? The cylinder infinitely long?
Yes.
Negative E times change in x.
So the electric field's not constant. Then, because we got that R in there.
Is the integral E dot df
Negative.
negative?
dr in this particular case. So my electric field, so if we integrate from my inner to outer radius there, so let's come up with some clever labels here. Call this R sub I for inner radius. What the heck? R sub O for outer radius. Where do I come up with this stuff? Genius. So we're going to integrate from our inner to our outer. Now my electric field is in the direction of dr. I'm going in that direction, and so I can conveniently get rid of my dot products there and do the negative integral from r initial to r outer e dr. And I got my formula right there. So negative lambda over 2 pi epsilon naught times the integral of dr over r. which is negative lambda over 2 pi epsilon sub naught. I got lazy right there, let's write the limits of integration back in, times the natural log of r from r initial to r outer, sorry, r inner to r outer, which is negative lambda 2 pi epsilon sub naught. Natural log of r outer, we'll throw in the intermediate step, r outer minus natural log of r inner. And it depends on what form you want it in. Typically, if you got the difference of natural logs, or logs in general, you go ahead and combine it. So I got negative lambda over 2 pi epsilon sub naught, natural log of r outer over r inner. That is the potential difference between my positive and negative cylinder. Lambda is my charge per unit length. So negative q over 2 pi epsilon sub naught L over natural log, or times natural log of r outer minus r inner. So that's equal to delta V. But I want Q over delta V. So Q over delta V. So bringing V down, everything else up. Or so this becomes 2 pi epsilon sub naught L over natural log of r outer over r inner. Making sure that, oh, that direction. Now, when you're looking at the potential, I got the negative sign right there. Let's just sort of double check. Because I went from the inner to the outer, went from the positive to the negative in the direction of the electric field. Typically, when you're looking at the voltage, when I'm looking at this equation right here, you're going from the negative to the positive plate. In other words, you want a positive potential. But let's just make sure that what we have right here is a negative number. So when I take the minus sign away, I still have a positive number. Obviously, 2 pi are positive numbers. And that's the math people have been lying to us and everyone else. Epsilon sub naught is a positive number. Length is a positive number. Negative length doesn't really have much meaning here. So it comes down to this. Is the natural log of r outer over r inner a positive or negative number? How do you know?
You can't take the L in the negative number.
Sorry, let me rephrase the question. Is the natural log of that positive or negative? Ro over ri, I agree, is a positive number, but is the natural log of it going to be positive?
Yes.
Okay, why?
The value is less than 1.
The value is less than 1?
RO over RI.
Is,
When you plug it into ln.
are you saying r over ri is less than 1?
Yeah.
Austin, is that a look of, I don't know the answer, or what is Mario saying? He sounds crazy.
Well, RO would be bigger than RI. So it'd be greater than 1.
It would be greater than 1.
Never mind.
No problem. When is the natural log of what equals 0?
1.
So as long as it's bigger than 1, it's a positive number, which it is. And so therefore, my capacitance is going to be 2 pi epsilon sub naught L over the natural log of RO over RI.
So you just get rid of the negative sign?
Yeah. Because capacitance is a positive number. Although I wouldn't put it past, there's probably some engineer out there who's come up with some meaning of a negative capacitance, or theoretical physicists come up with a meaning for a negative capacitance. So the main point of this, one, got to do a little calculus, which is always enjoyable, but the fact that this is sort of the standard equation when we're doing this. We'll do the same thing with the spherical capacitor. We'll do this formula, we'll solve for delta V, and we'll all feel better about the world. All right, the spherical capacitor. Make the inside positive and the outside negative, so these are spheres. So this has some surface charge density sigma, and this has some surface charge density of negative sigma. My electric field will be going away from the center. And the electric field is dependent upon the charge of this inner sphere. It does not depend upon the outer sphere, because for the same reason as we've derived before and talked about before, or Gauss's law, that the even distribution of charges on the outside does not have, basically creates an electric field of 0 in the middle. My electric field KQ over R squared, R hat. Actually, I wrote sigma there, but really there's no reason to have sigma. Actually, we don't want sigma. I apologize for that. This should be Q. This should be negative Q. If they had just opposite surface charge densities, then the outer sphere has a higher charge. And that's not what I want. So Q and negative Q. I know that the potential difference between the two is, well, which way are we going? We're going to go from inner to outer or outer to inner?
Inner to outer.
Okay? It doesn't matter, we just need to make sure we're doing it, which way we're doing it. So if we go from inner to outer, we will end up with a negative potential difference, and that's fine, we'll just get rid of the negative sign at the end. I feel like half this course is trying to figure out, when can I just ignore the negative sign, and when do I have to pay attention? So negative integral, electric field and dr are in the same direction. So this just becomes KQ over R squared dr from R inner to R outer. So this becomes negative KQ over R from R inner to R outer. So this becomes KQ times 1 over R outer minus 1 over R inner. Is this fraction right here positive or negative? Sorry. Is this difference of fractions a positive or negative number? Why? I agree with that. But is 1 over R outer bigger than 1 over R inner? Yeah, this is a bigger number here, so the fraction is smaller. So this is a negative number, as we would expect that the voltage would decrease, potential would decrease as you go from the positive to the negative side. let's get in terms of a common, in terms of a single fraction. So I have KQ times R inner minus R outer divided by the common denominator, R inner, R outer. So that's my potential. Back to here. I went Q divided by that. Well, there's my Q right there. And that's equal to delta V. So this would be R inner, R outer over K times R inner minus R outer. And those are the two most common non-parallel plate capacitors that you face in the course. Occasionally someone might throw in a toroid hole. But I will not make you do that. I had a student years ago ask me what the capacitance was of a of that capacitor.
Toroidal?
Yeah, I don't know why it's difficult for me. There are just certain words that just, at least I can say nuclear, but cinnamon is another word that I struggled with for years. Anyway, you were asking a question, Lawson?
I was gonna say, what's an example of a spherical capacitor? Like, do we have one? Like,
I don't have an actual, here's the perfect place to put it. I don't have that. As a physicist, I don't have to know any practical applications for anything. That's the nice thing about it.
So what does that look like? Just I'm wondering.
What would it?
toroidal?
Yeah.
It's like a donut.
Yeah. Why they don't call it donut shape, I don't know.
To make it easier on you, you could just call it a donut.
Yeah, the donut, okay. The donut capacitor. Yeah, so basically, think of the cylindrical capacitor. I was trying to remember